Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Now, I want you to imagine something with me for a moment. Picture Earth 4 billion years ago, this wild, untamed planet where life is just beginning to figure itself out. Volcanic gases are hissing across barren rocks, lightning is splitting ancient skies, and in these warm, primordial pools, the very first cells are struggling to exist. It's like nature's first rough draft, you know? Everything is experimental, everything is new. But here's where our story takes a fascinating turn. In the timeline I'm about to share with you, something crucial is missing from this ancient scene. Something so small you'd need the most powerful microscopes to even see it, yet so important that without it, the entire story of life on Earth would unfold completely differently. What's missing? Viruses. Those tiny genetic pirates that normally slip between cells like smuggled goods, carrying information from one organism to another. In our alternate Earth, they simply don't exist. Not a single one. Now, I know what you might be thinking. Wait, isn't that a good thing? No viruses means no diseases, right? Well, hold on to that thought, because what I'm about to tell you will completely flip that idea on its head. Let me paint you a picture of just how significant this absence really is. In our world, there are 10 to the 31st viral particles floating around our planet. That's 10, followed by 31 zeros. To put that in perspective, that's 10 million times more viruses than there are stars in the entire observable universe. 10 million times. Think about that for a second. Every grain of sand, every drop of water, every breath of air around you is teeming with these microscopic entities. And here's what's really wild. Your own body right now, as you're listening to this, carries 380 trillion viruses at any given moment. They're not just hanging out there doing nothing, they're part of your story, part of what makes you, you. In fact, 8% of your DNA, 8%, comes from ancient retroviruses that integrated into your ancestors' genomes millions of years ago. But in our virus-free timeline, that 8% simply isn't there. And let me tell you, the consequences of that missing genetic material are absolutely staggering. Picture this scene. It's 1892, and we're with Dmitry Ivanovsky, a Russian botanist who's studying diseased tobacco plants. In our world, this is the moment when humanity first discovers viruses. Ivanovsky finds these mysterious invisible agents causing tobacco mosaic disease. But in our alternate timeline, when he looks through his microscope and filters, he finds nothing. Just healthy plants and normal bacteria. The invisible world that should be there simply doesn't exist. Now, you might think, well, that's great for the tobacco plants. But here's the thing. Those viruses weren't just causing disease. They were serving as nature's genetic messengers, carrying innovations between organisms in ways that would have profound consequences for all life on Earth. Let me walk you through what's really happening in those primordial pools 4 billion years ago. In our world, these early cells are constantly being invaded by viruses. It sounds violent, and in a way it is, but it's also incredibly creative. Every time a virus infects a cell, it's like a genetic remix happening in real time. The virus might pick up a useful gene from one cell and deliver it to another. Maybe a gene that helps with energy production, or one that provides resistance to harsh chemicals, or even one that allows the cell to process new types of food. This process, scientists call it horizontal gene transfer, is like nature's internet. Instead of genetic information only passing from parent to offspring, it can jump sideways between completely unrelated organisms. A bacterial cell might suddenly acquire a gene that originally came from an ancient organism living near underwater volcanic vents. That gene might give it the ability to survive in boiling water, or to eat sulfur, or to produce a completely new type of protein. But in our virus-free world, that genetic internet is down permanently. Every innovation, every breakthrough in survival, every clever adaptation that a cell develops stays locked within that specific lineage. It's like having the most brilliant inventors in the world, but no way for them to share their discoveries with anyone else. The numbers here are just mind-blowing. In our world, up to 18% of bacterial genomes come from this kind of viral-mediated gene transfer. 18%. That means nearly 1/5 of the genetic instructions that make bacteria who they are came from viral messengers carrying genes between species. In our alternate timeline, bacteria are working with significantly less genetic material, and they're entirely on their own. Here's where it gets really crazy. Remember those cyanobacteria I mentioned? The ones that would eventually flood our planet with oxygen? In our world, they evolved pretty early on, around 2.5 billion years ago. They figured out how to harvest energy directly from sunlight, and in the process, they started pumping out oxygen as waste. This might not sound dramatic, but this oxygen revolution completely transformed our planet. It's what made complex life possible. But here's the thing, that ability to photosynthesize, to capture sunlight and turn it into energy, it didn't just evolve once. The genetic innovations that made it possible spread between different types of bacteria through viral carriers. It's like one bacterial inventor figured out solar power, and viruses help distribute that technology to bacterial communities all over the planet. In our virus-free timeline, that distribution system doesn't exist. So, when one group of bacteria finally evolves photosynthesis, the innovation stays put. Other bacterial communities have to reinvent the wheel independently, and most of them never figure it out at all. The result? Those oxygen-producing cyanobacteria don't appear for an extra billion years. A billion years! That's twice as long as complex life has existed on our planet. And when they finally do show up, their oxygen revolution unfolds in slow motion. Instead of rapidly transforming the atmosphere, oxygen levels creep up gradually over hundreds of millions of additional years. The great oxygenation event that normally happens around 2 billion years ago gets pushed back to maybe 1 billion years ago, and it's much weaker. Now, you're probably wondering what this means for complex life, the plants and animals and fungi that we're familiar with. Well, here's where our story takes an even more dramatic turn. Complex cells, the ones with nuclei and organized internal structures, which scientists call eukaryotes, these are the building blocks of everything we think of as complex life. In our world, they evolved around 2 billion years ago, not long after oxygen levels started rising. But in our virus-free timeline, they're showing up 2 billion years late. 2 billion years. Think about what that means. If complex cells don't evolve until 1 billion years ago, instead of 3 billion years ago, then everything we know, every plant, every animal, every fungus, is running on a completely different schedule. The Cambrian explosion, when complex life really took off and diversified into all these amazing forms, that gets pushed so far into the future that it might be happening right now in our present day. But here's the most shocking part, and this is something that really blew my mind when I first learned about it. Those retroviruses I mentioned earlier, the ones that contributed 8% of your DNA, they didn't just add random genetic material. Some of that viral DNA became absolutely essential for life as we know it. There are these proteins called syncytins, and they come from ancient retroviruses that infected our mammalian ancestors around 100 million years ago. Now, here's what's wild about syncytins. They're what make placentas possible. Without these viral-derived proteins, mammalian mothers can't create the specialized cells that allow a developing baby to share the mother's blood supply and nutrients. So, in our virus-free world, this innovation never happens. Mammals, including the lineage that would eventually become humans, they're stuck being egg layers. No live births, no nursing, no extended parental care. The entire evolutionary strategy that made mammals so successful simply can't evolve. Picture this. It's 65 million years ago, and that massive asteroid hits Earth, wiping out the dinosaurs. In our world, small mammals survive and quickly diversify to fill all the empty ecological niches. But in our virus-free timeline, those mammals are still essentially reptiles that produce milk. They can't give birth to live young, they can't nourish developing babies in the womb, and they don't have the reproductive flexibility that normally allows mammals to thrive in changing environments. The result? The age of mammals never really arrives. Reptiles and birds continue to dominate terrestrial ecosystems. The evolutionary innovations that led to elephants and whales and primates and eventually humans, they're either severely delayed or they take completely different forms. And speaking of humans, here's something that'll really make you think. There's a gene called ARC that's absolutely crucial for learning and memory formation. Every time you form a new memory, this gene is activated in your brain cells. And guess what? ARC comes from an ancient retrovirus. It's viral DNA that became so important for brain function that we can't survive without it. In our virus-free world, human ancestors, if they even evolve at all, would have fundamentally different cognitive abilities. The very mechanisms that allow you to remember this conversation, to learn new information, to form long-term memories, might work in completely different ways or might be severely limited. But let's zoom back out to the bigger picture for a moment. I want you to really think about what we're talking about here. In our normal timeline, viruses have been the great genetic mixers of our planet for billions of years. They've been carrying innovations between organisms, forcing rapid evolution, creating the biological diversity that makes Earth such a vibrant, resilient place. Without them, evolution becomes this lonely, isolated process. Each species is climbing its own mountain, but there are no bridges connecting the peaks. No sharing of innovations, no rapid adaptation to changing conditions, no biological internet carrying solutions from one part of the tree of life to another. The Earth that emerges from this alternate timeline is recognizable in some ways. There are still bacteria, there are still simple plants and animals. But it's operating at maybe 10% of its normal genetic innovation rate. Life is simpler, more predictable, and ultimately more fragile. Here's what really gets me about this whole scenario. We usually think of viruses as these destructive forces, right? They cause diseases, they disrupt our lives, they're generally seen as the bad guys in the story of life. But when you imagine a world without them, you realize they're actually the invisible architects of complexity itself. Every pandemic that's shaped human history, every viral infection that's driven evolution, every genetic innovation that's been spread by viral carriers, it's all part of this larger story where destruction and creation are intimately connected. The viruses that challenge us are the same ones that gave us the genetic tools to meet those challenges. Fast forward 100 million years into our virus-free timeline, and something deeply unsettling becomes clear across Earth's biosphere. Picture this. You're looking at a world where every single breakthrough in survival, every clever adaptation, every innovation that could save a species stays locked in a genetic prison. There are no viral messengers to carry these life-saving discoveries between organisms, no genetic highways connecting different forms of life. It's like living in a world where every inventor works in complete isolation. Imagine if the person who discovered fire could never share that knowledge with anyone else. If the inventor of the wheel had no way to spread that innovation. If every medical breakthrough, every technological advance, every solution to a problem died with its creator. That's exactly what's happening in the microscopic world of our virus-free Earth. Let me tell you about something that should have happened in the Archean oceans around 3 billion years ago. In our normal timeline, this is when a particular group of bacteria makes one of the most important discoveries in the history of life. They figure out how to harvest energy directly from sunlight. This innovation, photosynthesis, is absolutely revolutionary. It's like discovering nuclear power when everyone else is still burning wood. Now, in our world, viruses would grab this innovation and spread it like wildfire. Within years, maybe decades, viral messengers would carry the genes for photosynthesis to bacterial communities across the planet. It's nature's version of open-source technology. One breakthrough immediately becomes available to countless other organisms, but in our virus-free timeline, that sharing network doesn't exist. So when this one group of bacteria evolves photosynthesis, the innovation stays put. The neighboring bacterial community, maybe just a few feet away in the same ocean, has no way to acquire this life-changing ability. They have to start from scratch and evolve it independently, which could take millions or even hundreds of millions of years. Most of them never figure it out at all. The numbers here are staggering when you really think about them. In our world, the genes for photosynthesis spread so rapidly through viral transfer that cyanobacteria, of those oxygen-producing powerhouses, appear relatively quickly and start transforming our planet's atmosphere around 2.5 billion years ago. But in our alternate timeline, this process takes an extra billion years, a billion years of delay, and when photosynthetic bacteria finally do appear in significant numbers, their oxygen revolution unfolds in slow motion. Instead of rapidly flooding the atmosphere with oxygen, creating the great oxygenation event that makes complex life possible, the process drags on for hundreds of millions of additional years. The oxygen levels that should spike dramatically instead creep upward at a geological pace. Here's what's really wild about this delay. It pushes back the entire timeline of complex life by billions of years. Those eukaryotic cells, the complex cells with nuclei that form the basis of all plants, animals, and fungi, they don't evolve until around 1 billion years ago instead of 2 billion years ago. That means every form of complex life we know is running on a completely different schedule. But the most shocking absence in our virus-free world is something called horizontal gene transfer. Now, I know that sounds like scientific jargon, but stick with me because this is mind-blowing stuff. In our normal world, viruses are constantly moving genes between completely unrelated species. Not just between similar bacteria, but between bacteria and plants, between plants and animals, between organisms that are so different they might as well be aliens to each other. Think about some of the incredible biological mashups that exist. In our world, because of this viral gene shuffling, there are sea slugs that can photosynthesize. They've stolen genes from the algae they eat and incorporated them into their own bodies. Imagine an animal that can live off sunlight like a plant. There are bacteria that can digest plastics using enzymes that originally came from fungi. There are aphids that produce their own sunscreen using genes they acquired from fungal partners through viral messengers. These biological mashups sound like science fiction, but they're everywhere in our world. Up to 18% of bacterial genomes, nearly 1/5 of their genetic instructions, come from this kind of viral-mediated gene transfer. 18%. That's like saying nearly 1/5 of everything that makes bacteria who they are came from genetic material that viruses carried between species. In our virus-free timeline, none of this cross-species innovation happens. Every organism is stuck with only the genes it inherits from its direct ancestors. There's no mixing, no borrowing, no genetic collaboration across the tree of life. Evolution becomes this lonely, isolated process where each species has to solve every problem independently. Picture what this means for biological innovation. In our world, when one organism evolves a clever solution to a problem, maybe resistance to a toxic chemical, or the ability to digest a new food source, or a more efficient way to process energy, that solution can spread to other organisms through viral carriers. It's like having a planetary research network, where every breakthrough immediately becomes available to anyone who needs it. But in our virus-free world, that research network is down. When an organism in one part of the planet evolves resistance to a particular toxin, Organisms facing the same toxin elsewhere have no way to access that solution. They either evolve their own resistance independently, which could take millions of years, or they go extinct. The result is a biosphere that operates at maybe 10% of its normal innovation rate. Life becomes predictable, conservative, and fragile. Without the constant genetic mixing that viruses provide, organisms can't rapidly adapt to changing conditions. They can't quickly develop new capabilities when opportunities arise. They're essentially stuck in genetic stagnation. Here's something that really drives this home. Imagine you're a bacterial cell living near an underwater volcanic vent. The environment is incredibly harsh: boiling water, toxic chemicals, crushing pressure. In our world, you might acquire genes from other extremophile bacteria through viral transfer, genes that help you survive in these conditions. Maybe genes for heat-resistant proteins, or enzymes that can neutralize toxic metals, or molecular pumps that help you deal with the pressure. But in our virus-free world, you're on your own. You have to evolve every single adaptation from scratch. The bacterial community living around a different volcanic vent, facing similar challenges, can't share their solutions with you. Each community becomes isolated, solving the same problems independently and inefficiently. The cascade effects of this genetic isolation ripple through the entire history of life. Those cyanobacteria that finally evolve photosynthesis can't share their innovation widely, so oxygen production remains limited to small pockets of the ocean. The great diversification of bacterial life that normally happens in the Archean and Proterozoic eras is severely stunted. And here's what's particularly heartbreaking about this scenario. When environmental challenges do arise, and they always do, whether it's climate change, asteroid impacts, or volcanic eruptions, organisms don't have the genetic diversity to respond quickly. In our world, viral gene transfer creates this vast reservoir of genetic solutions that life can draw upon during crises. But in our virus-free timeline, that reservoir doesn't exist. Think about it this way. Evolution normally operates like a massive genetic library, where viruses are constantly checking out genetic books from one section and depositing them in another. Solutions discovered in the extremophile section get shared with the marine section. Innovations from the soil bacteria section get passed to the plant section. It's this incredible system of genetic collaboration that makes life incredibly resilient and creative. But in our alternate timeline, each section of the library is locked off from all the others. The extremophiles keep their heat-resistant secrets to themselves. The marine bacteria can't access the innovations developed by their soil-dwelling cousins. The plants have no way to borrow useful genes from bacteria or fungi. Every organism is working in isolation, reinventing the wheel over and over again. The most profound realization is that this isn't just about efficiency, it's about the fundamental nature of life itself. In our world, life is this collaborative, interconnected web, where innovations flow freely between the most unlikely partners. Viruses don't just spread disease, they spread solutions. They're the invisible threads that weave the tree of life into a single, interconnected network. Without them, that network fragments into millions of isolated islands. Each species becomes a fortress, self-contained, but cut off from the vast ocean of genetic innovation that surrounds it. Life becomes simpler, more predictable, and ultimately more vulnerable to the inevitable changes that sweep across our planet. As we continue forward in our virus-free timeline, we'll see how this genetic isolation affects every aspect of life on Earth, from the functioning of immune systems that never learn to fight, to ocean ecosystems that lack their crucial population control mechanisms, to human civilization that develops without the viral pressures that normally shape our evolution. But for now, just imagine what we've lost: a planet where genetic innovations flow freely between organisms, where life constantly reinvents itself through collaboration, where solutions discovered by one form of life immediately become available to all. In our virus-free world, that biological internet of gene transfer has been permanently disconnected, leaving life to struggle alone in the vast silence of genetic isolation. Now, let me tell you about something happening inside your body right this very moment. As you're listening to this, 10 billion T cells are patrolling through your bloodstream and tissues, each one trained through what can only be described as a brutal education system. These cellular soldiers can recognize millions of different threats, mount sophisticated attacks, and remember enemies they've fought before. It's like having an army where every soldier is also a detective, a special forces operative, and an intelligence analyst all rolled into one. But here's what's absolutely mind-blowing. This incredible defense network exists specifically because viruses taught it how to fight. Every sophisticated feature of your immune system, every clever strategy, every rapid response, every molecular weapon evolved as a direct response to viral pressure. In our virus-free world, none of this happens. The greatest teacher of biological warfare simply doesn't exist. Picture this scene 300 million years ago, in the early days of vertebrate evolution. Our ancestors are simple fish-like creatures swimming in ancient seas, and they're facing a crisis they don't even know they have. In our normal timeline, these early vertebrates are under constant assault from viruses. Every day brings new viral challenges, new strains, new attack strategies, new ways that viruses try to hijack cellular machinery. This viral pressure is like having the world's most demanding personal trainer, one who never lets up, never gets easier, and constantly invents new challenges. And just like intense physical training builds stronger muscles, this constant viral warfare builds stronger immune systems. Generation after generation, only the vertebrates with the most sophisticated defenses survive to reproduce. But in our virus-free timeline, that personal trainer never shows up. These early vertebrates face only the slow-changing threats of bacteria and fungi. Without the intense pressure of rapidly evolving viral adversaries, their immune systems plateau at a primitive level. They develop basic defenses, maybe slightly better than a castle wall with a few guards, but nothing approaching the sophisticated networks we see in our world. The numbers here are just staggering. Your immune system right now can produce 10 to the 18th different antibodies. That's a billion unique molecular weapons. Each one is specifically designed to recognize and neutralize a different threat. It's like having a key for every possible lock, a tool for every possible job, a solution for every possible problem. This vast arsenal exists because viruses mutate incredibly rapidly, up to 1 million times faster than their hosts evolve. Imagine facing an enemy that changes its appearance completely every few days, that constantly develops new weapons and new strategies. That's what our ancestors faced with viruses, and it forced the evolution of immune systems that could keep up with this breakneck pace of change. But in our virus-free world, organisms face threats that change slowly or predictably. Bacteria might evolve new toxins over thousands of years. Fungi might develop new infection strategies over tens of thousands of years. Without the lightning-fast pace of viral evolution driving adaptation, vertebrate immune systems settle for maybe 10,000 different antibodies, enough for the slow-changing bacterial and fungal threats, but nowhere near the sophisticated arsenal that normally develops. Here's where it gets really fascinating. Remember that brutal education system I mentioned? It takes place in an organ called the thymus, located just behind your breastbone. Every day, millions of new T cells are produced in your bone marrow, but before they're allowed to join your immune system, they have to pass through thymus training. And what an education it is. These young T cells are exposed to thousands of different molecular fragments, pieces of viruses, bacteria, fungi, and even your own body's proteins. They have to learn the crucial skill of distinguishing self from non-self. T cells that attack your own tissues get eliminated immediately. T cells that can't recognize foreign invaders also get rejected. Only about 2% pass this brutal screening process. But here's the thing. This sophisticated training program evolved specifically to deal with viral threats. Viruses are masters of molecular mimicry. They can disguise themselves to look like your own cells, or they can hide inside your cells while subtly changing the molecular signatures on the cell surface. Teaching T cells to detect these subtle changes requires incredibly sophisticated education. In our virus-free world, that education system never develops its full complexity. The thymus remains a simple organ that provides basic training for basic threats. T cells learn to recognize obvious bacterial and fungal invaders, but they never develop the nuanced skills needed to detect sophisticated molecular disguises. The result is an immune system that's easily fooled and slow to respond. And speaking of responses, let me tell you about natural killer cells, one of my favorite parts of the immune system. These cells patrol your body like security guards, checking the ID badges that every cell displays on its surface. Healthy cells display a full set of normal identification molecules, but when a cell gets infected by a virus, those ID badges change in subtle ways. Natural killer cells evolve to spot these changes instantly. They can detect when a cell's surface molecules are even slightly different from normal, and they immediately destroy the infected cell before the virus can reproduce. It's like having security guards who can spot a fake ID from across the room. But guess what happens in our virus-free timeline? Without virus-infected cells to train on, natural killer cells never develop their sophisticated detection abilities. They might evolve to recognize obviously damaged or cancerous cells, but they lack the fine-tuned sensitivity that normally makes them so effective. They're like security guards who can only spot the most obvious troublemakers while missing the subtle threats. The inflammatory response is another crucial part of immunity that develops differently in our alternate world. In our timeline, inflammation is this carefully orchestrated process that's been fine-tuned over millions of years of viral battles. When tissues get infected, immune cells rush to the scene, blood vessels dilate to allow more immune cells through, and the whole area becomes a battlefield where immune cells fight invaders. This response has been calibrated through countless viral infections to be strong enough to fight off invaders but not so strong that it destroys healthy tissue. It's like a controlled explosion, powerful enough to clear out the bad guys but precise enough not to level the entire neighborhood. But in our virus-free world, this calibration never happens. The inflammatory response remains crude and often does more harm than good. Without the constant feedback from viral infections, immune systems never learn the delicate balance between fighting hard enough to win and fighting so hard that you destroy yourself in the process. Perhaps most shocking of all is what happens to adaptive immunity, the ability to remember past infections and mount faster, stronger responses when the same threat appears again. This is why vaccines work, why you usually don't get the same virus twice, why your immune system gets better at fighting specific threats over time. In our world, this system evolved to deal with the incredible diversity of viral threats. Every viral infection teaches your immune system something new, and that lesson gets stored in long-lived memory cells that can survive for decades. It's like having a vast library of enemy intelligence that gets more comprehensive with every battle. But in our virus-free timeline, adaptive immunity develops in a severely stunted form. Without the incredible diversity of viral antigens to learn from, the system never reaches its full potential. Memory responses are weak and short-lived. The sophisticated network of memory B cells and T cells that normally provides lifelong protection never fully develops. Think about what this means for the organisms living in our alternate timeline. Every infection they survive teaches them very little about fighting future infections. They can't build up the robust immune memory that normally makes older animals more resistant to disease. Each threat they encounter is almost like facing it for the first time. And here's something that really drives home the importance of viral pressure. the entire system of immune regulation. In our world, immune systems have to walk this incredibly fine line between being strong enough to fight off viruses and being so strong that they attack healthy tissue. This has led to the evolution of sophisticated regulatory mechanisms, molecular brakes that can dial down immune responses when they're no longer needed. These regulatory systems are crucial because viral infections often require very strong immune responses. Without proper regulation, these responses would continue indefinitely, causing autoimmune diseases where the immune system attacks its own body. But in our virus-free world, immune systems never face threats severe enough to require strong responses, so they never evolve sophisticated regulation either. The result is organisms with immune systems that are simultaneously too weak to fight serious threats and too poorly regulated to avoid causing collateral damage. They're like armies that have never been in a real war. They lack both the weapons and the discipline that come from facing serious adversaries. As we move forward in our virus-free timeline, we'll see how these immunologically naive organisms fare when faced with environmental challenges. Without the biological boot camp that viral infections normally provide, life remains vulnerable in ways that go far beyond just lacking antiviral defenses. The entire architecture of biological resilience, the systems that normally make life tough, adaptable, and quick to recover from setbacks, never fully develops. And that sets the stage for some truly catastrophic vulnerabilities that we'll explore as our alternate Earth continues to evolve in the absence of its most important teachers. Every single day in our oceans, an absolutely massive massacre unfolds that most people never think about. Right now, as we speak, marine viruses are killing between 20 and 40% of all ocean bacteria. We're talking about 10 to the 23rd bacterial cells being destroyed daily. That's a number so large it's almost meaningless, until you realize this represents more living organisms than there are stars in. Thousands of galaxies. This isn't just random destruction, though. This daily bacterial apocalypse is actually the engine that drives ocean chemistry, ocean food webs, and ultimately, the oxygen you're breathing right now. In our virus-free timeline, this engine simply doesn't exist, and the consequences transform Earth's oceans into something almost unrecognizable. Picture the Pacific Ocean as you know it, that vast expanse of deep blue water where you can see for hundreds of feet down, where sunlight penetrates to illuminate coral reefs and kelp forests. Now imagine instead a Dacheng Beasley, thick, murky soup where visibility is measured in inches rather than feet. The water has the consistency of thin pudding, teeming with so many bacteria that it's more like swimming through liquid yogurt than through clear seawater. This is what happens when you remove ocean viruses from the equation. Without their constant population control, bacterial communities explode in numbers beyond anything we can imagine. In our world, viruses act like invisible shepherds, constantly culling bacterial flocks to keep them at manageable levels. But in our alternate timeline, those bacterial flocks are free to multiply without limits. Here's what makes this scenario so dramatic. Marine bacteria reproduce incredibly fast when conditions are right. Some species can double their population every 20 minutes. Every 20 minutes! Without viral predators keeping them in check, bacterial blooms that normally last days or weeks in isolated areas become permanent, planet-wide phenomena. The numbers are absolutely staggering. Marine viruses normally release 150 gigatons of carbon annually when they burst open bacterial cells. To put that in perspective, that's more carbon than all the fossil fuels humans have ever burned throughout our entire industrial history, every single year. This massive release of organic matter, which scientists call the viral shunt, is what keeps ocean nutrients cycling properly. When viruses kill bacteria, they're not just removing the bacteria, they're releasing everything inside those bacterial cells back into the water. All the carbon, nitrogen, phosphorus, and other nutrients that the bacteria had accumulated get redistributed to other organisms. It's like a massive recycling program that operates 24 hours a day, 7 days a week, across every ocean on the planet. But in our virus-free oceans, this recycling program shuts down. Bacteria become these massive nutrient hoards, locking away crucial elements like iron and phosphorus inside their cells. Instead of nutrients flowing freely through the ecosystem, they get trapped in bacterial bodies that just keep multiplying. Think about what this means for ocean food webs. In our normal oceans, tiny zooplankton microscopic animals about the size of a grain of rice feed on bacteria and other microorganisms. These zooplankton are absolutely crucial because they're the base of the entire marine food web. Small fish eat zooplankton, larger fish eat small fish, and so on up to whales and sharks. But here's the thing. Zooplankton evolved to eat bacteria that had been weakened or killed by viral infections. They're like scavengers that clean up after viral battles. In our virus-free oceans, bacteria are too numerous, too hardy, and too aggressive for zooplankton to handle. It's like trying to eat a meal that's actively fighting back and winning. The zooplankton populations crash within decades, and when the zooplankton disappear, everything that depends on them follows. Small fish that normally consume millions of zooplankton daily find themselves with nothing to eat. The herring, sardines, and anchovies that support much of ocean life simply vanish. Without small fish, larger predators have nothing to hunt. The cod, tuna, and salmon that normally patrol open waters find empty seas. And without these mid-level predators, the great marine giants, the whales that can consume 4 tons of krill daily, never evolve at all. The largest animals our planet has ever produced simply cannot exist in seas dominated by bacterial soup. But the most terrifying changes happen in ocean chemistry itself. Remember those cyanobacteria that produce about 50% of the oxygen you're breathing? In our normal oceans, they thrive in the nutrient-rich waters created by viral recycling. But in our virus-free seas, they're completely overwhelmed by faster-growing bacterial competitors. Picture this. Cyanobacteria are like small, efficient solar panels that convert sunlight to energy while producing oxygen as a byproduct. But they're not particularly aggressive competitors. In our world, viruses constantly knock back their bacterial competition, giving cyanobacteria the space and nutrients they need to flourish. In our alternate timeline, those bacterial competitors never get knocked back. They multiply exponentially, consuming all available nutrients and blocking sunlight from reaching the cyanobacteria below. It's like covering all the solar panels with thick blankets. The oxygen production machinery is still there, but it can't function. The result is a catastrophic crash in ocean oxygen production. Within centuries, marine oxygen levels drop to perhaps 5% of normal levels. Vast regions of the ocean become anoxic dead zones, where nothing larger than bacteria can survive. The biological pump that normally cycles oxygen between the oceans and atmosphere stutters and fails. And here's where things get really scary. In our world, bacteria that grow unchecked often produce toxic byproducts. Hydrogen, sulfide, methane, ammonia, these are the chemical signatures of bacterial overgrowth. In small concentrations, these compounds are manageable. But when bacterial populations explode across entire ocean basins, the chemical composition of seawater itself changes. Imagine oceans that smell like rotten eggs from hydrogen sulfide production, waters that bubble with methane gas, coastal areas where the smell is so intense that land animals can't venture near the shore. This isn't science fiction, it's what happens when bacterial ecosystems grow without viral regulation. The cascade effects reach far beyond the oceans themselves. Those marine bacteria that normally get recycled by viral action represent enormous reserves of carbon and other elements. In our virus-free world, Instead of being recycled, this organic matter sinks to the ocean floor in massive quantities. Over millions of years, this creates thick layers of bacterial sediment on the ocean floor. The carbon that should be cycling through marine ecosystems gets locked away in these sedimentary deposits. Ocean productivity, which depends on nutrient cycling, crashes to levels that can't support complex food webs. But perhaps the most profound change is in the very nature of marine evolution. In our world, the constant viral pressure in oceans drives rapid evolutionary adaptation. Marine organisms evolve sophisticated defenses, complex behaviors, and intricate ecological relationships. The oceans become these incredibly diverse, dynamic ecosystems where every niche is filled with specially adapted organisms. In our virus-free oceans, that evolutionary pressure largely disappears. The seas become dominated by a few highly successful bacterial species that face no significant predation. Diversity plummets. Innovation stagnates. The oceans that should be teeming with millions of different species become monotonous bacterial monocultures. Picture Earth's blue marble from space, but instead of the vibrant blues and greens that indicate healthy, diverse oceans, you see murky browns and yellows, the colors of bacterial blooms that never end. The seas that gave birth to life become simplified, toxic, and ultimately hostile to the very complexity they once nurtured. This is what happens when you remove the ocean's executioners. Those marine viruses that kill trillions of bacteria daily aren't agents of destruction. They're the invisible gardeners that maintain the delicate balance necessary for ocean life. Without them, the seas transform from dynamic ecosystems into stagnant bacterial cultures, fundamentally altering the chemistry of our planet and making the evolution of complex marine life essentially impossible. As we'll see in our next chapter, this ocean transformation has profound implications for the development of biotechnology and medicine, as humanity loses access to the marine-derived discoveries that normally revolutionize our understanding of life itself. The year is 1970, and Hamilton Smith is peering through his microscope at something remarkable. He's watching bacteria defend themselves against viral attack, witnessing molecular warfare at the cellular level. What he's about to discover will launch the entire biotechnology revolution: restriction enzymes, molecular scissors that can cut DNA at precise locations. These bacterial weapons, evolved to slice up invading viral DNA, will become the foundation tools that allow scientists to manipulate genes, create new medicines, and eventually sequence entire genomes. But in our virus-free timeline, this pivotal moment never happens. Smith looks through his microscope and sees the peaceful bacteria. No viral invasions, no molecular warfare, no need for sophisticated DNA-cutting weapons. And without these viral defense tools, humanity enters the genetic age with essentially Bronze Age equipment. Let me walk you through what we've lost. Those restriction enzymes that Smith discovered, they're like incredibly precise molecular scissors that can cut DNA at exact sequences. Imagine trying to perform surgery with a butter knife instead of a scalpel. That's what genetic engineering looks like without these viral-derived tools. In our world, by 1972, Paul Berg uses these viral-inspired tools to create the first recombinant DNA. He takes genes from one organism and inserts them into another, creating the first genetically modified organism. This breakthrough opens the door to producing human insulin in bacteria, creating growth hormones for children with deficiencies, and manufacturing countless other life-saving medicines. But in our virus-free timeline, Berg has no molecular scissors to cut DNA precisely, no viral vectors to carry genes between organisms, no understanding of how genetic material naturally moves between cells. The biotechnology revolution that should transform medicine gets stuck at the starting line. The human cost of this delay is staggering. Right now, millions of diabetics depend on human insulin produced by bacteria that carry inserted human genes. In our alternate world, They're still relying on insulin harvested from pig and cow pancreases, supplies that are limited, expensive, and sometimes cause allergic reactions. The 8,000 Americans who've been cured of sickle cell disease through viral-delivered gene therapy continue to suffer from this devastating condition. Here's what's particularly heartbreaking. The solutions exist, but humanity lacks the tools to implement them. Scientists in our virus-free world understand that genetic diseases are caused by faulty genes. They know that replacing those genes could cure the diseases. But without viral vectors to deliver healthy genes into cells, gene therapy remains a theoretical concept rather than a practical treatment. Think about Kary Mullis in 1983, developing the polymerase chain reaction PCR that allows scientists to amplify tiny amounts of DNA into quantities large enough to study. This technique becomes absolutely crucial for genetic research, forensic science, and medical diagnostics. But PCR depends on heat-resistant enzymes that were originally discovered in bacteria living around volcanic vents, bacteria that evolved these enzymes specifically to survive viral attacks at extreme temperatures. In our virus-free world, those bacteria never faced viral challenges at high temperatures, so they never evolved heat-resistant enzymes. Mullis can still develop PCR, but it's painfully slow and inefficient. Instead of amplifying DNA in a few hours, the process takes days or weeks. The Human Genome Project, which normally takes 13 years with viral-derived tools, stretches into a century-long endeavor. The medical catastrophe deepens when we consider what happens with vaccines. In our world, many vaccines are created using weakened or modified viruses. We understand how to manipulate viral genetics because we've studied how viruses naturally manipulate genetics. But in a world without viruses, the entire concept of vaccination develops along completely different lines. When the first major pandemic hits our virus-free world, maybe a bacterial plague or a deadly fungal infection, scientists can't quickly develop effective vaccines. They lack the deep understanding of how to stimulate immune responses that comes from studying viral infections. The tools for rapid vaccine development, all derived from viral research, simply don't exist. And here's where it gets really frustrating. When COVID-19 arrives in our alternate timeline caused by bacteria or fungi instead of a virus, humanity faces it with medieval medical knowledge. The mRNA vaccines that saved millions of lives, they're based on understanding how viruses deliver genetic instructions into cells. Without viruses as teachers, scientists never learn these delivery mechanisms. The technology to package genetic instructions and deliver them precisely into specific cell types comes directly from studying viral biology. Those lipid nanoparticles that carry mRNA into your cells in COVID vaccines, they're engineered versions of viral delivery systems. In our virus-free world, scientists might eventually develop vaccines, but they'd be crude, slow to produce, and far less effective. CAR-T therapy provides another devastating example. This revolutionary cancer treatment takes immune cells from patients, genetically modifies them to better recognize cancer cells, then returns them to the patient to fight the disease. It's been incredibly successful for certain blood cancers, offering hope to patients who had run out of other options. But CAR-T therapy relies entirely on viral vectors to deliver genetic modifications into immune cells. Scientists use modified viruses that have been engineered to carry therapeutic genes, instead of harmful ones. In our virus-free timeline, this entire approach is impossible. The vehicles for delivering genetic modifications simply don't exist. The losses cascade through every aspect of biotechnology. Monoclonal antibodies, which treat everything from cancer to autoimmune diseases, are often produced using viral-infected cell lines. Protein production for pharmaceuticals relies heavily on viral promoter sequences that drive high levels of gene expression. Even basic research tools like green fluorescent protein, which allows scientists to track genes and proteins in living cells, was discovered in organisms that use fluorescence to communicate about viral infections. But perhaps the most profound loss involves our understanding of life itself. In our world, studying viruses has revealed fundamental principles about how genetic information flows, how cells communicate, how immune systems function, and how evolution operates. Viruses are like molecular machines that demonstrate the basic mechanics of life in their simplest, most elegant forms. Without viruses to study, our virus-free civilization develops a fundamentally incomplete understanding of biology. They might eventually discover DNA and RNA, but they'd miss crucial insights about how genetic information can be packaged, delivered, and expressed. They'd understand inheritance, but miss the horizontal gene transfer that shapes evolution. They'd develop medicines, but lack the precision tools that make modern biotechnology possible. The irony is heartbreaking. In trying to imagine a world free from viral diseases, we've created a world where humanity lacks the tools to fight any diseases effectively. The very entities we often think of as purely harmful turn out to be essential teachers, showing us the molecular mechanisms we need to develop effective treatments. By the 21st century, in our virus-free timeline, while our world is revolutionizing medicine through viral-inspired biotechnology, their world is still struggling with basic challenges that we solved decades ago. They can sequence DNA, but slowly. They can produce some medicines, but inefficiently. They understand genetics, but incompletely. The synthetic biology industry, worth $500 billion in our world by 2025, never emerges in their timeline. The bacteriophage therapy that could replace antibiotics as superbugs spread remains undiscovered. The gene drives that could eliminate malaria-carrying mosquitoes are inconceivable without understanding viral genetics. Most tragic of all, when climate change accelerates and new diseases emerge as they inevitably do, our virus-free humanity faces these challenges with tools that are centuries behind what they should be. They're fighting 21st century problems with 19th century solutions, all because they never had viral teachers to show them the molecular strategies that make life truly adaptable and resilient. As we'll see in our next chapter, this technological limitation profoundly shapes how human civilization itself develops, creating a world where medical challenges that should be manageable become civilizational threats, and where the genetic tools that normally help humanity adapt to changing conditions remain permanently out of reach. The year is 70,000 BC, and a small band of early humans stands at the edge of Africa, preparing for a journey that will ultimately populate the entire planet. But in our virus-free world, their odyssey unfolds along dramatically different paths. Without viral diseases creating natural barriers, driving migrations, and shaping human evolution through selective pressure, our species' expansion follows patterns that would be completely unrecognizable to us. Think about what normally drives human migration. In our timeline, viral pandemics regularly devastate populations, creating empty territories that survivors can colonize. Disease outbreaks force people to flee infected areas, spreading human populations into new regions. Viral infections create evolutionary pressure that favors certain genetic traits in different environments. But in our virus-free world, none of these driving forces exist. Picture those early humans leaving Africa. In our timeline, they face a gauntlet of new diseases as they encounter different climates, different animals, and different microbial environments. Each new territory presents viral challenges that force rapid adaptation. Only the most genetically diverse and immunologically robust populations survive to establish new settlements. But in our alternate timeline, human expansion becomes a much more gradual, peaceful process. Without viral diseases creating population bottlenecks, human groups don't face the intense selection pressure that normally shapes our species. The genetic bottleneck that reduced humanity to perhaps 10,000 individuals around 70,000 years ago, likely caused by viral pandemics and environmental stresses, never happens. This sounds positive at first, right? No devastating population crashes, no mass suffering from disease. But here's what's fascinating. Those bottlenecks actually made humanity stronger. When populations crash and only the most adaptable individuals survive, it concentrates beneficial genetic traits. It's like evolution's way of stress testing the human genome and keeping only the most resilient versions. Without this stress testing, human populations in our virus-free world remain larger but more genetically uniform. They don't develop the sophisticated immune systems that come from surviving viral challenges. They don't evolve the cognitive adaptations that help humans deal with rapidly changing, unpredictable threats. In many ways, they remain closer to their original African ancestors, lacking the diversity that normally comes from adapting to viral pressures across different continents. Fast forward to 1347 AD, and we encounter one of history's most transformative events, except in our virus-free world, it never happens. The Black Death arrives in Europe and kills 1/3 of the population, fundamentally reshaping society. Labor becomes scarce, so surviving workers can demand higher wages and better conditions. The rigid feudal system that had dominated Europe for centuries suddenly becomes unsustainable. This demographic catastrophe, horrible as it was, actually triggered the Renaissance. Abandoned villages reverted to forests, creating new ecosystems. Labor shortages drove technological innovation as people looked for ways to be more productive with fewer workers. Social mobility increased as traditional hierarchies collapsed. The intellectual revolution that produced Leonardo da Vinci, Galileo, and the scientific revolution all emerged from the social upheaval caused by viral pandemics. But in our virus-free timeline, the Black Death never occurs. European feudalism persists for centuries longer, without the demographic shock that normally breaks it apart. Those abandoned villages that became forests, creating the fungal networks that scientists study today, remain continuously inhabited. The social revolutions, sparked by disease-driven labor shortages, never ignite. The consequences ripple through every aspect of human development. Without pandemic-driven social upheaval, technological innovation proceeds at a slower pace. The printing press might eventually be invented, but without the social demand created by post-plague educational reforms, it spreads slowly. Universities don't expand rapidly to train new clergy and administrators to replace plague victims. The entire intellectual awakening that we call the Renaissance gets delayed by centuries. Here's something that really shows how deeply viral infections have shaped human genetics. The CCR5 Delta 32 mutation. This genetic variant, carried by about 10% of pairing Europeans, provides significant resistance to HIV infection. It evolved because populations that survived previous viral pandemics, possibly smallpox or plague, were more likely to carry mutations that provided viral resistance. In our virus-free world, this mutation never evolves. When HIV eventually emerges in our alternate timeline, maybe as a bacterial infection with similar transmission patterns, European populations have no genetic resistance at all. The demographic impact is far more severe than anything we experienced, because their ancestors never faced the selective pressure that would have favored protective mutations. But the most profound differences involve the viral DNA that's normally integrated into human genomes. Remember that 8% of human DNA that comes from ancient retroviruses. In our virus-free world, that genetic material simply doesn't exist, and some of that viral DNA became absolutely crucial for human development. The ARC gene, essential for memory formation, comes from an ancient retrovirus. Every time you learn something new, every memory you form, depends on genetic machinery that was originally viral. In our virus-free timeline, human cognitive development follows completely different pathways. Maybe they develop alternative memory systems, or maybe their memory capabilities remain fundamentally limited compared to ours. Even more dramatically, the syncytin proteins that enable placental development are derived from ancient retroviruses. Without these viral origin proteins, mammals in our timeline, including humans, remain egg-laying creatures. Picture human civilization developing with fundamentally different reproductive biology. No live births, no extended pregnancy, no intricate mother-child bonding that occurs during gestation. This changes everything about human social development. In our world, the extended helplessness of human infants, combined with the intense bonding that occurs during pregnancy and nursing, drives the evolution of complex social structures. Extended families, cooperative child-rearing, complex communication, all of these emerge partly because human reproduction requires so much investment and cooperation. But in our virus-free world, where humans lay eggs and young develop independently, social structures evolve along completely different lines. Maybe humans remain more solitary, like many egg-laying species. Maybe they develop communal nesting behaviors instead of family structures. The entire foundation of human civilization rests on different biological principles. The numbers tell remarkable stories about immune system development. In our world, viral infections during pregnancy actually help train fetal immune systems. Exposure to maternal antibodies and controlled viral challenges prepare babies for the pathogenic world they'll inhabit. But in our virus-free timeline, this prenatal immune education never occurs. The result is devastating. Infant mortality rates reach 90% or higher. Without the immune training that normally occurs through maternal viral exposure, babies are born essentially immunologically naive. They have no defense against even mild bacterial or fungal infections. Human populations can barely maintain themselves, let alone expand and thrive. This creates a completely different demographic pattern. Instead of the population growth that normally drives human expansion and technological development, our virus-free humans struggle just to maintain stable numbers. Societies organize entirely around child survival rather than growth and exploration. The resources that normally go into art, science, and culture get devoted almost entirely to keeping enough children alive to continue the species. Even the migrations that do occur follow different patterns. In our world, humans spread along coastlines, partly because marine environments offered new food sources, but also because ocean currents carried different, viral challenges that selected for adaptable populations. Inland migrations often followed river systems that provided both transportation and distinct disease environments. But in our virus-free world, human migration is driven entirely by resource availability and climate. There's no viral selection pressure favoring coastal populations with stronger immune systems. There's no advantage to genetic diversity that comes from surviving different disease environments. Human expansion becomes more predictable but also more vulnerable to environmental changes. When climate shifts occur, as they inevitably do, our virus-free human populations lack the genetic diversity and adaptive mechanisms that normally help species survive environmental challenges. They've been living in a biologically stable world, and they're not prepared for the chaos that environmental change brings. The civilizations that eventually emerge are fundamentally different from ours. Without the constant threat of viral pandemics, they don't develop the medical knowledge that drives much of human scientific advancement. Without the social upheavals caused by disease-driven demographic changes, their societies remain more static and hierarchical. Perhaps most importantly, they never develop the biological understanding that comes from fighting viral infections. They don't discover the principles of vaccination, the mechanisms of immunity, or the genetic tools that allow rapid adaptation to new challenges. When environmental crises eventually arrive, they face them with limited biological knowledge and inflexible social structures. The humanity that emerges from our virus-free timeline is recognizable but limited, like a musical composition missing several octaves, or a painting created with only half the available colors. They survive. They even thrive in their own way, but they never reach the adaptive complexity that viral challenges normally drive in our species. Standing at the threshold of tomorrow, our virus-free Earth faces a future as alien as any distant planet. The biological revolution that should be transforming the 21st century, built entirely on viral tools and insights, never arrives. The gene therapies curing genetic diseases, the synthetic biology industry is worth hundreds of billions of dollars, the bacteriophage treatments that could replace failing antibiotics, all of these remain locked away in a future that can never arrive. Let me paint you a picture of what the 21st century looks like in our alternate timeline. It's 2025, and while our world has companies engineering custom organisms to produce medicines, clean up pollution, and even manufacture materials, their world is still struggling with basic biotechnology challenges that we solved decades ago. CRISPR gene editing, that revolutionary tool that allows precise modification of DNA, never develops because it's based on bacterial immune systems that evolved to fight viruses. In our world, scientists discovered that bacteria use molecular scissors to cut up viral DNA, then adapted those scissors for their own purposes. But in our virus-free timeline, bacteria never developed such sophisticated DNA cutting tools because they never needed them. The result is a world where genetic diseases remain largely incurable. Children born with cystic fibrosis, sickle cell disease, or muscular dystrophy face the same bleak prognosis their counterparts faced 50 years ago in our timeline. The gene therapies that now routinely cure these conditions simply cannot be developed without the viral-derived delivery systems and editing tools that make them possible. But the deeper changes run beneath technology's surface, affecting the very nature of how life evolves and adapts. Picture this. Climate change arrives in both timelines, bringing rising temperatures, shifting weather patterns, and new environmental stresses. In our world, organisms have been shaped by billions of years of viral pressure that taught them to adapt rapidly to changing conditions. Coral reefs facing warming oceans can acquire heat-resistant genes from bacteria through viral transfer. Forest trees threatened by new diseases can rapidly evolve resistance by incorporating genetic solutions discovered by other plants. The constant genetic mixing that viruses provide creates a vast reservoir of adaptive potential that life can draw upon during crises. But in our virus-free timeline, this reservoir doesn't exist. When coral reefs face warming temperatures, they have no mechanism to quickly acquire heat-tolerance genes. They bleach and die permanently, unable to adapt at the speed that climate change demands. Forests, confronting new fungal diseases, can't rapidly develop resistance because there's no system for sharing defensive genes between trees. The numbers paint a stark picture of biological limitation. Earth's biosphere in our virus-free timeline operates at perhaps 10% of its normal genetic innovation rate. The quadrillion viruses that should be shuffling genes between organisms like a massive planetary casino are absent. Instead of this dynamic genetic marketplace, life becomes predictable, stable, and ultimately fragile. Think about what this means for biodiversity. In our world, the constant viral pressure drives rapid speciation as organisms adapt to new challenges. Islands of genetic innovation emerge wherever viral pressures create new selective environments. But in our virus-free world, evolution proceeds at geological pace. Species change slowly, predictably, and with far less creativity. The biological resilience that comes from constant viral challenges, what we might call the anti-fragility of life, never develops. Organisms become like muscles that have never been exercised, immune systems that have never been challenged, minds that have never been questioned. They function adequately in stable conditions but lack the strength that comes from adversity. When the first major catastrophe strikes, maybe an asteroid impact like the one that killed the dinosaurs, maybe a supervolcanic eruption like the Toba explosion, life in our virus-free world faces it with limited adaptive capacity. In our timeline, the survivors of such catastrophes rapidly diversify to fill empty ecological niches, their evolution accelerated by viral-mediated gene transfer. But in our alternate world, recovery proceeds with agonizing slowness. The human species in this timeline faces particular vulnerabilities. Without the sophisticated immune systems that evolve from viral pressure, they remain susceptible to environmental challenges that our humans learned to handle millions of years ago. When new bacterial or fungal diseases emerge, as they inevitably do, our virus-free humans lack the immunological tools to respond effectively. Their medical technology, limited by the absence of viral-derived biotechnology tools, can't develop effective treatments quickly enough. What should be manageable disease outbreaks become civilizational threats. The genetic diversity that normally helps human populations survive epidemics is absent because viral selection pressure never concentrated beneficial traits. Perhaps most profoundly, the very nature of biological innovation changes in our virus-free world. In our timeline, life is constantly surprising us with new solutions, unexpected adaptations, and creative responses to challenges. The tree of life is more like a web, with genetic innovations flowing freely between the most unlikely partners through viral messengers. But in our alternate timeline, that web fragments into millions of isolated threads. Each species becomes a genetic island, cut off from the ocean of innovation that surrounds it. Life becomes more like a museum than a laboratory, beautiful, ordered, and preserved, but ultimately static. The technological implications extend far beyond biology. In our world, studying viral replication has taught us principles of nanotechnology, self-assembly, and molecular machinery that inspire countless innovations. But in our virus-free timeline, these concepts remain undiscovered. The technological revolution that biotechnology normally drives never occurs. Synthetic biology, the engineering of custom organisms to solve human problems, remains rudimentary because scientists lack the sophisticated understanding of genetic programming that comes from studying viruses. The production of medicines, fuels, and materials using engineered organisms proceeds slowly and inefficiently compared to our world. Even agriculture develops differently. In our timeline, plant breeders use viral vectors to introduce beneficial genes into crops, creating varieties that can resist diseases, tolerate harsh conditions, or provide better nutrition. But our virus-free world lacks these tools, leaving agriculture vulnerable to the environmental challenges that climate change brings. The cascade effects reach into space exploration as well. In our world, astrobiologists studying extremophile bacteria often focus on organisms that evolved their remarkable capabilities, partly through viral-mediated gene transfer. Understanding how life adapts to extreme conditions helps us prepare for finding life on other planets or even engineering organisms that could survive in space. But our virus-free timeline lacks this deep understanding of biological adaptation. Their space exploration programs, when they eventually develop, are less informed about the possibilities of life in extreme environments. They're less prepared to recognize life that might exist in forms very different from Earth's virus-free biology. As we look toward the far future of our alternate timeline, we see a world that's fundamentally different from ours, not just in technology or biology, but in the very nature of how change and adaptation occur. It's a world where life never learned to dance with chaos, where stability became more important than resilience, where safety took precedence over growth. What emerges is not necessarily a worse world, but certainly a simpler one. A world where biological innovations spread slowly, if at all, where each species faces challenges in isolation, where the creative chaos that viruses normally bring to evolution is replaced by a more orderly, but ultimately more limited form of change. Our journey through this virus-free timeline reveals a profound truth that reshapes how we think about the microscopic world around us. Those viral particles that we can't see, that sometimes make us sick, that seem so destructive and threatening, they're actually the invisible architects of life's complexity. They're the ancient teachers that showed evolution how to be creative, the molecular messengers that connected all life in a single, dynamic network. They taught our immune systems how to fight by being worthy opponents. They gave us the genetic tools to adapt by constantly presenting new challenges. They connected the tree of life into a web of innovation by carrying solutions between the most unlikely partners. They're the reason life on Earth became anti-fragile instead of merely resilient. In imagining their absence, we discover their true significance. Viruses aren't just parasites or pathogens, they're evolution's greatest innovators, the tiny tyrants whose cruelty created strength, the invisible architects whose constructions made all complexity possible. Without them, Earth remains forever young, forever simple, and forever vulnerable. With them, life becomes an endless symphony of creativity, adaptation, and resilience. And understanding that difference might just change how we see every microscopic challenge we face in our own very viral, very vibrant world.